Hi, welcome back. In this short lecture, I want to provide a little bit more explanation about the notebook, the Python notebook that you can find in Canvas, describing on how to implement the Quantum SVM using Pennylane. So the problem we are trying to solve is a binary classification problem using the wine recognition dataset. We will use the scikit-learn wine recognition dataset that we can load directly from scikit-learn. So this is a label dataset with the information about different kind of wine. In totals, it has 13 numerical variables, and these labels correspond to the kind of wine. There are 3 possible labels, so we're going to ignore one because we want to have a binary classification problem. So we are left with a dataset for a binary classification problem. So instead of having the 3 initial labels, we dropped one and we just focus on classifying either one label or the other one, making a binary classification problem. In order to load the dataset, we can just call the function load wine, and then we put in x and y vector. So we have set return x, y to true, so that we also get the labels here in y. So the wine recognition dataset needs a little bit of the pre-processing because we want to make a binary classification problem. It turns out that first 59 elements in the dataset must belong to the first category, what we call label 0, while the 71 subsequent ones must belong to the second one label. So in order to use only 2 labels, we get the first 130 elements in our dataset. So because we want to ignore the third category, so we can just run the following piece of code. Therefore, we have a label dataset with only 2 categories, which allow us to solve a binary classification problem. The first things when preparing for training an SVM, since we also want to test the results, we split our dataset into training dataset that we're going to use during the optimization step, during the training step, and also we're going to leave a part of the whole dataset just for testing. So to test what is the accuracy of the training and test how good is in generalizing. For doing that, we can call again a function from scikit-learn. In this case, it's called train test split. It's a function that allows to split the whole dataset in a part that is used for training and a part that is used for testing. In this case, we use 90% of the dataset just for training. Whenever we want to ingest a dataset, the dataset might have a quite large range. So it's very convenient to normalize the dataset between a certain value, for instance, between 0 and 1. So also we can compare different features across the same range. In this case, we scale each of the variables linearly, and we can use that by using the scikit-learn function called maxAppScaler. It is an object from scikit-learning pre-processing part. Since all our variables are positives, all the values in our training dataset will be between 0 and 1. In case there were negative values, or a scalar variable will be taking the values between -1 and 1 instead. Then we need to normalize the test dataset using the same proportion as the train dataset, and this can be achieved by the following piece of code. So we use scalar.transform. So note that we use the same scalar object as before here, but the function is different. Before we called the transform method instead of the fit transform. So in this case we use transform, but before we use fit transform. In this way, the scalar uses the proportion that is saved before. In addition, we run an instruction to clut the values in the test dataset just between 0 and 1. In case our test dataset has value that go larger than 1, since we are using the same scaling used for the training dataset. So it's also important to cut if there are some values in the test trainer set that are outside the normalization part. Let's go a little bit now in the quantum part. So we look at the pre-processing, that is something we've seen before if you've done any machine learning. So let's see at the encoding part, that is also what we call the feature mapping, that we go from the data in the classical to the quantum state, and we use the feature map. So our data set has 13 features that corresponds to 13 variables. So if we are using angle encoding or ZZ feature map on 13 variables, would require us to use 13 qubits. It's feasible, but the simulation, the training part, since we're using quantum computer simulator in Pennylane, will be quite long. So it's better to use a smaller number of qubits. So instead, we can use the amplitude encoding, and this will allow to use only 4 qubits. So 4 qubits allow us to have 2 to the 4 quantum states, so 16 qubits. So the feature maps can accept up to 16 qubits. So we can encode these 13 variables for other features in 16 inputs that are our quantum state. So we have 13, we have 16 available. So what we can do, we can fill the remaining ones with 0, and Pennylane allow us to make it quite easy. So remember that the way to describe a quantum circuit in Pennylane is to define a function. In this case, we call our function kernel underscore circ, and then we take the 2 data points, in this case A and B. Together with information about the quantum circuit, we associate a device, and we can do that by adding a decorator with a @qml node, and then we provide our device. Our device in this case is a device with 4 qubits, and then we use the default quantum circuit simulator. So the first part of our kernel is to apply a feature map that corresponded to amplitude embedding, and we encode A. And you see here we pad with 0, and we provide also the number of qubits, that is A. So the first part of our quantum circuit is just to apply the quantum circuit corresponding to an embedding of A. The second part is to apply the adjoint of the B embedding, right? So we have the first part of the circuit, that is a simple feature map with amplitude encoding using as parameter A. And the second one is the adjoint operation of the amplitude embedding of the B that is acting on the quantum state resulting from this first amplitude embedding. And then what we do, we return the probability of a different state, and this is obtained by returning qml.probes, and we can get results from all the qubits. So to summarize, the amplitude embedding returns an operation equivalent to the amplitude encoding of its first argument. In our case, we use the arrays of A and B in the first argument. We use qml.adjoint to compute the adjoint or inverse of the amplitude encoding of B, acting on the resulting of the first embedding circuit. Finally, we retrieve an array with the probabilities of measuring each possible state on a computational basis, and we are going to take the first element of this array, that is the probability of getting 0 value in all the qubits. This is the very nice, straightforward way to calculate the kernel product using this inverse technique that we saw in the previous lecture. So we did the circuit. So now we got to combine the training part with the quantum kernel we had defined using Pennylane. Scikit-learn has its own implementation, as we see, of support vector machine that take as input a custom kernel. This custom kernel will be our quantum feature map circuit. So to use a custom kernel, we are required to provide a kernel function accepted two arrays A and B and returning a matrix JK containing the kernel applied to AJ and BK. Once the kernel is prepared, the SVM can be trained using the fit method. So in this case here, what we're going to do is to define a quantum kernel taking as an input A and B, and basically creating this matrix by just applying our feature mapping. So we're looping over A and B to provide this argument, and then we apply our quantum circuit to create this matrix. Once we created this matrix, we can feed in the qkernel as a custom kernel, and we call the fit function acting on this training dataset where we have the feature in X and then the labels in the Y, the label in the Y underscore TR part. So this is easy and to do. You will see in the Python notebook. You are welcome to try and check yourself and experiments with different things in the notebooks. If you try that, then using this amplitude encoding, you can check what is the accuracy. You will find an accuracy of 92%. This is the last slide of this lecture, and talk to you soon.